Okay, I'll be talking to you about ripples in space-time, a new area in astronomy that has opened up with the detection of gravitational waves from faraway distant universe. So, before I move on, let me tell you the context of this gravitational waves. As you know, that Newton's gravitational theory was an approximation. It was replaced by Einstein's general theory of relativity. Einstein's general theory of relativity is arguably the most beautiful as well as successful theory of modern physics. It is successful because it has matched all experimental tests of gravitation remarkably well till now. What happens with Einstein's gravitation is that space and time are combined into one entity called space time. This was special relativity, and in 1916, to include gravitation, Einstein postulated that matter curves space time, and so matter tells space time how to curve and space time tells matter how to move. So, how do we move in a curved space time? We actually follow straight lines. So, if you have masses in the universe like this yellow and red balls that you see, you can imagine them to be the sun and two planets. You can see each of them has warped the space around it, and the particles just move in a straight line. So, when we see that earth is going in an orbit, it is actually moving in a straight path in the curved space caused by the sun's mass. This is how we understand gravitation, not as a force, but as a manifestation of space-time curvature. Now, what happens when matter is in motion? So, matter is in motion, then the space-time fabric is churned up. So, I can show you this in a video, and you can see two neutron stars going around each other, and just like sticks on a surface of water, as they move towards each other, they orbit and start merging, you create ripples in the fabric of space time. The ripples go out as what are called gravitational waves, and they are actually a signal of this merger happening in the distant universe to an observer far away. So, what does Einstein's gravitation predict? And uniquely beyond Newton's gravity are these gravitational waves. So, matter in motion implies space-time ripples and fluctuations in the space-time curvature that propagate at waves, and these are very similar to waves that we are familiar with, say the electromagnetic waves, which are talked to as EM, and just as in electromagnetism, in GR the gravitational waves travel at the speed of light, and that means gravitational waves are massless excitations. They are transverse. So, the excitation is in the plane perpendicular to its propagation, and it has two states of polarization. So, here for example, is animation of how electromagnetic wave propagates to people who have seen this before. You have electric field fluctuating in two directions, and as the wave propagates, this wave carries with it this information about fluctuating electric field, electric and magnetic field in fact. For gravitational waves, this is a bit different. So, if you have a gravitational wave passing through space, and if you look at a cylinder, it actually moves like this surface that is seen moving in the next picture there, and it has two polarizations, not orthogonal to each other, but at 45 degrees from each other, where a ring of particles actually is deformed into an ellipse and back into a circle and an ellipse in the other direction, and there are two ways to do it, and as you can see the two patterns are 45 degrees from each other. These are the two polarizations. So, in some sense Newton's gravity replaced by Einstein's gravity gives you a unique prediction of these gravitational waves that are very similar to electromagnetism, but they nevertheless a bit different and something new, and they are fluctuations in the space-time curvature. So, there was already evidence for gravitational waves way back in 1994, the Nobel Prize was given for an observation of two pulsars going around each other. We could monitor the period of this pulsars and saw that the period was increasing and it was decreasing in fact, and the predicted rate of decrease matched what you would expect from emission of gravitational waves, calculated using Einstein's gravity. So, here is the spectacular graph which shows measured points with error bars matching a predicted curve from general relativity extremely well, and this fetched the Nobel Prize in 1993 to Hulse and Taylor for showing that gravitational waves do exist, but this was an indirect evidence. You saw it as missing energy and angular momentum. Here is what happens when two masses coalesce or merge in a distant part of the universe. So, here is a movie of two black holes in some distant part of the universe going around each other, and it shows you a representation of the space time around these masses. So, as we zoom in, you see that around each of those two black balls the space time is warped. So, there is this big well, gravitational potential well around each of the masses, as you would expect in Newtonian theory too. What you do not expect in Newtonian theory are these arrows of space time flux, and that is again something entirely new that Einstein's gravity gives you. As these two masses move around each other, they are churning up space time, and you can see that the pattern of stakes is getting richer till they come to a point where the black holes just touch each other and are ready to merge. So, this is when the movie will be frozen and they touch each other and sort of there is a burst. This is the merger of the black holes, and then a new black hole is formed, or a single black hole which sort of settles down, sheds off all its kind of asymmetry and settles down into a spherical shape. And you can see that gravitational waves racing out from this event. So, when we are at Earth and observing gravitational waves, what do we see? So, in two distant detectors placed 3000 kilometers away from each other on US soil, on September 14 the following signal was seen. You could see two waveforms that are shown in the two panels at LIGO Hanford and Livingston. They are identical, and there is also a power diagram which shows you the power in different frequency bands at different times in this event. And if you had paid attention to the sound accompanying it, I will play this again to, and you can see there is a bloop. This thing is called a chirp, and this is a telltale signature of mergers happening in the universe through gravitational waves. And mergers do happen in very different ways, and they happen such that if the masses are different, they can give you very interesting sounds. So, I will play a few bits for you here of sounds. Here was a tweet, almost like a bird sound, and then a little later a slightly higher pitch, and then something that is absolutely quick, blip, right. So, these are called chirps, just dramatic name or poetic name given to these signals, and it is very easy to calculate what the form would be for different kind of masses of objects merging. So, the discovery of the century happened on September 14th, and it was declared to the world on September 5th, 2016. So, it took about 6 months to verify everything, and what we had seen were two black holes merging to give you one black hole with an accompanying chirp signal. So, this was the launch of gravitational wave multi-messenger astronomy, and it also sort of gave rise to a field where different messengers of astronomy from different areas came together to follow up these signals. This does a lot of cosmology too. and these were the first measurements of the expansion rate of the universe, and also they kind of provided cosmic answers to where the gold in the universe was formed, and these were formed in such collisions of neutron star binaries. So, the LIGO detections thus far have been the following. So, I am just playing for you the different chirps forms that have been seen till now. You can see there were short ones which are seen at the top, 4 of them, 5 of them, and then there is this yellow one which keeps going on, and this was the neutron star binary merger that was detected just a year back, I mean last year in August in fact. So, this is how it stands in terms of detecting these, what we know about them in terms of detections and gravitational waves from the distant universe in different merger scenarios. And this is going to get richer with more observations coming up in the future observing runs of LIGO and other LIGO like instruments that are coming up all over the world. So, the gravity wave spectrum that we have measured till now is one end of the spectrum, just like electromagnetic waves come in various different frequencies. So, you have radio waves of low frequency going up to optical and ultraviolet and then going up to X-rays and gamma rays. Similarly, gravitational waves are seen at different scales and different length scales of periods depending on the phenomena involved in the universe, and this spans all the way from cosmological signals from right from the beginning of the universe to these mergers of black holes on the right hand side, which are detected by LIGO. So, in the next 15 years, 4 windows of gravitational wave astronomy are expected to open up. One has already opened up, which is the discovery of binary black hole mergers and neutron star mergers by LIGO in 2015. There are other experiments which are being planned. So, in the 2030s, there will be a space based gravitational wave detector called LISA that would see a different class of merger objects and bring in a new window again into the universe, new spectrum of the window. And there is also another window through pulsar timing array, which is expected to open up any time now in the coming decade. And finally, probably the most exciting possibility of seeing gravitational waves right from the birth of the universe, which is expected to be seen in CMB polarization. So, let me move on to how we detect ripples in space time. So, this is where, before I tell you what is involved in detection, let me tell you what is involved in the creation of these waves. So, when I showed you this chirp waveform of the first detection, what had happened were 2 black holes, one 30 times the mass of the sun, another 40 times the mass of the sun, went around each other and crashed into each other pretty violently and produced another black hole which was about 70 solar masses. And if you look at the plot of the velocity as the distance changed in the last few orbits, you would see that in fact as the orbit shrunk, your velocities of these 30 solar mass black holes reached almost the third the speed of light. So, enormous speeds which are attained by elementary particles in accelerators, here they are attained by huge objects which are 30 solar masses in weight and mass, and such massive things are moving almost at the speed of light and crashing into each other. Imagine the violence of this. So, it is an extremely violent phenomena, and not surprisingly in this phenomena almost 3 sun equivalent of mass is converted into gravitational wave energy, and these are the most energetic events that you see in the universe. These are far more energetic than any electromagnetic phenomena that we have seen. So, essentially you can see that it produces a 10 to the power of 49. So, 10 followed by 49 zeros watts of energy in that little bit of time that it took to merge. So, obviously, these are the most exotic and most violent phenomena that are being seen in these gravitational waves. However, although the phenomena is so violent, so much energy is involved in it, what we see is a very tiny signal, and that is because, as we said, mass curves space time, but it curves it by a very little amount. It requires a lot of mass moving at very high speeds to do something really dramatic to space time. So, the biggest signal that we had, or the signal we had to play with to detect this, was involving displacements measurements at the level of 10 to the minus 18 meters. This almost sounds impossible, because 10 to the power minus 18 meters is far smaller than the size of an atom, and even few orders of magnitude smaller than the size of a nucleus. So, here is a movie which shows you a little dramatic show of electrons going around the atom. This is the atomic scale at 10 to the minus 10 meters, a tenth of a nanometer, and then you go to femtometers where you see the nucleus, and what we are trying to measure are displacements where things are moving at the level of few times 10 to the minus 18 meters. So, how do we achieve such a thing? So, in doing this, this field had to develop technology which sort of pushed the boundaries of measurement in length. So, what you see in the dashed box are the typical length scales that we encountered in day to day life. So, you may have gone on a holiday about few thousand kilometers. So, that is about a megameter, right. So, 10 to the 6 meters, or you may measure something small at the level of millimeters. That is the normal scales that we worry about. And what we have learnt in physics are atomic scales, as I told you, 10 to the minus 10, and nuclear scales 10 to the minus 15. But here we are stepping beyond, well beyond our zone of comfort in going and trying to measure length changes at the level of 10 to the minus 18 meters. And hence, this discovery, as was heralded as the discovery of the century, fetched a Nobel Prize immediately in the following year, and 3 people were noted for that. There was also a special breakthrough award given to this. And very interestingly, this discovery paper had substantial participation from India. There were 37 authors from 9 Indian institutes, and at this point about 100 Indian researchers, 80 to 100 Indian researchers are working on this. So, how do we detect gravitational waves? So, when gravitational waves go through space time, they kind of are like this wave that you see in the left. So, if you have a lattice of points, the distance between them changes, and if you monitor a ring of particles, the ring actually deforms into an ellipse and back into a circle and an ellipse in the other direction. And the best tool we have to detect displacements of this kind or monitor changes in position at this level are interferometers, and this is something that many of you may be familiar from your undergraduate physics, is a typical Michelson interferometer. So, you have a laser light coming in, it is split into 2 directions at 90 degrees to each other, they go and reflect off a mirror far away. If these mirrors are exactly same distance away from the center, there is no light at the photodetector port, and if you displace any of the mirrors or both, you will see light because change of interference pattern. Here is a movie to illustrate that. Here is a laser shining into a beam splitter and laser light going to the top and to the right in along 2 arms, reflecting back in the mirror, and then the interference pattern is monitored on the photodiode. And if I run the movie, you will see as I move the length of the 2 arms relative to each other, the amount of light that leaks into the photodiode changes, right, and that is the signal that we are looking for. So, let me play it again, and you can see that as the length of the arms changed, you had different amount of light. A better or more detailed rendition of that is given here, where laser shines light on the beam splitter, goes to the two mirrors, comes back. Everything is set up such that when the mirrors are not moving, there is no light at the photodiode, but when the mirrors move, you have light, little bit of light in the photodiode. And this is actually a very high precision measurement, because what we are looking for is change in interference pattern at a trillionth of a radian of the phase of the waves. So, here you can see the mirrors moving and light at the photodiode changing, and this is the way we detect gravitational waves, because gravitational waves stretch the arm in one direction while bringing it in the other direction, and then reverses the signal, and we see a pattern of change of light in the mirrors. However, to attain the 10 to the minus 18 meters of sensitivity, you need massive interferometers. So, typically you have seen Michelson interferometers in laboratories, which are at the best a meter in length. Here you have interferometers of 4 kilometers arm length. So, here are two pictures of operational interferometers in the US, the LIGO Hanford and the LIGO Livingston site, and here is a fly pass through one of the detectors. This is the Livingston detector, just to tell you and give you an idea of the scale. So, here is the center building that you see, and we will soon fly through the arms and look at the detector in its full scale glory. So, you can see this is an immense structure where you have vacuum tubes going all the way to the 4 kilometer end stations, and then light in fact travels along these vacuum tubes, gets reflected, comes back to the central station, where you have that photodiode and the laser, and of course, the people who monitor everything. And this sort of gives you a feel for what a mammoth scale physics apparatus is required to achieve this kind of sensitivity to changes of length at the level of 10 to the minus 18 meters. So, here are few nice shots from LIGO labs, and this is from the Hanford site, showing you the scale of things. So, there are people working within the vacuum tube, there are huge chambers which are bigger than people, and a mammoth scale thing. Apart from the mammoth scale apparatus at large, there are extremely subtle things that need to be done to make sure that you see small signals. So, in fact, the mirrors need to be very carefully isolated from ground vibrations, and that is done through stack of isolations that you see in the left side. You can see mirrors, 2 layers of mirrors hanging from the top of an active isolation platform. The mirrors are actually hanging on glass wires which are welded at the top, and each of these things are have to be done so carefully so as not to introduce any noise that can swamp out a very tiny signal. The suspension has to be such that it actually reduces the ground vibrations by 12 orders of magnitude. Okay, so, the ground at any place on earth vibrates at micron level, micrometer level, and you have to hit it with a factor of 10 to the minus 12 to make sure that you can hope to measure fluctuations at the level of 10 to the minus 18. It involves very advanced seismic isolation systems with very low noise sensors, actuators, and these are kind of the state of the art in any field of science and technology in the world. So, these are unique designs, and they provide new benchmark for what you can do with these. The mirrors that are involved have to be fantastic. They are 40 kilometer single crystal mirror, and they have surface accuracy of about a fraction of a nanometer, very low absorption for a 40 kilogram mirror. And if you want to compare the surface specs, these are about 100 times better than the best telescopes that you have in the world. The surfaces have to be that better, that good. And these mirrors are such that they have to be cast in one country, coated in another country, polished in a third country, and that is because no single country has the capability on all three at the level required. Here is a picture of the laser room. It is a bunch of amplifiers of the laser power, and it's a mastery of optics that allows you to produce a very narrow line width laser. It is a continuous laser at about 180 watts, but what is very important about it is that the frequency is stable and the intensity is stable at parts per billion. And these are again unique designs and unique lasers in the world that only are needed for this kind of a kind of frontier quest in science. We also do something very fancy. If you really think about it, a 40 kilogram mirror has not only thermal noise and mechanical noise, but we know that the world is quantum around us, and a 40 kilogram mirror itself has quantum fluctuations. We know that we are all quantum at some level. We do not see the quantum fuzziness around us because we are massive, but we see that around an electron because the electron is very light. But here we are trying to look at length scales of 10 to the minus 18, where quantum fluctuations of a 40 kilogram mirror in fact becomes comparable to the kind of displacements we are looking at, and we can take advantage of that to use what is called quantum measurements, and we can actually improve our measurements using something called squeezed light, and this is actually a frontier area for many applications in cold atoms, in quantum cryptology, and various other areas of quantum mechanics. So, let me now next move to the topic of what are we doing about gravitational waves in India. The Indian initiative, which is a LIGO India mega science project that is already ongoing. So, here is an Indian quest that is already underway. It has 4 lead institutes involved: the Rajaramana Center for Advanced Technology in Indore, the Institute for Plasma Research in Gandhinagar, Inter-University Center for Astronomy and Astrophysics in Pune, and also the Directorate of Construction of the Department of Atomic Energy. So, this is essentially a project, national project. It is one of the mega science projects and hence jointly funded by both the Department of Atomic Energy and the Department of Space and Time, Department of Science and Technology. And the institutions involved in this Indo-US collaboration are the LIGO labs in Caltech and MIT in the US, and these 4 institutes that I talked about in my little back from India. And why do we want to set up a detector here? That is because if you really think about it, we know that gravitational waves can be detected. Yes, we have detected gravitational waves from the distant universe in mergers of black holes and neutron stars, but with 2 detectors we do not have a very good ability to tell which part of the sky they came from. Hence, we cannot do astronomy with it. Now, if you look carefully at this figure, you would see that the error bar on the sky when you have only 2 detectors is this large banana shaped area, and if we have a third detector in India, that shrinks to this little peanut at the center. So, LIGO India is expected to make a big difference when it comes up, because it provides a huge baseline, and essentially the ability to point in different directions in the sky, which is shown in the left without LIGO India and on the right with LIGO India, are dramatically different. And what we expect when LIGO India comes up is to launch gravitational wave astronomy, where every detection of gravitational wave event in the universe can be followed up by other astronomical observatories, because we will be able to tell them where to point them in the sky. and that is essentially using something like triangulation, localization, which is used, for example, in triangulating your position on the in the city using GPS, or even the way we hear the direction of a sound, because our ears are apart, or we see the distance to, can gauge the distance to something that we see because our eyes are apart. Similarly, as you place gravitational wave detectors apart on the surface of the earth, you have higher and higher ability to deduce the direction from which the signal is coming. So, here is what will happen by 2024 when LIGO India comes up. There will be an array of gravitational wave detectors around the globe, and what we are seeing now are the 2 detectors in the US across the US continental divide, and then you have one in Japan coming up in a few years, and then LIGO India. And what is interesting, and then there is one in Europe, and what is interesting is if you look at the last column in the table below, LIGO India provides the biggest baseline or the separation to other detectors because of its geographical localization. As you may have guessed, so the LIGO India project is not just an astronomy project, it is far beyond that. So, if you look at the scope of what LIGO India touches, the boxes shown in green is the astronomy that it would enable, but then there are these boxes in yellow which enables fundamental science, and then boxes in purple which is all kinds of computational and big data science that you can do. But what is most attractive about this initiative of science, at the frontier of science, is the technology that it enables. The boxes in red are things that a country would kill to get into. I mean, these are really the highest end of technology in each of the areas mentioned in those boxes. So, hence it is not only an astronomy project, but it is a multidisciplinary project, and hence it was seeded by a multi-institutional consortium called INDIGO, Indian Initiative in Gravitational Wave Observations, set up in 2009, and this is this consortium that kind of put forward the LIGO India proposal. So, the LIGO India proposal, as I said, the main idea is a full exploitation of gravitational wave observations as part of astronomy. It brings in high end frontiers technology. We are banking on an Indian geographical advantage, but the rest of the world is banking on our demographic advantage. We are a youth dominated country, and hence will be growing this field much faster than most people could do, most other countries could have done. This provides immense opportunity for undergraduates and postgraduates across the country in science and technology, and hence is an amazing opportunity that teachers should be pointing out to their students as we go along. So, the project is a reality. It became a reality with the cabinet approval from the government in 2016 on February 17th, 2016. And you notice that the government does realize the immense potential of science and technology and engineering that this project would bring. So, it started with a big bang in the sense that immediately it was followed up by signing of the MOU, where the Prime Minister personally was present at the signing of the memorandum of understanding for this, and has been followed up at the top level ever since. It is one of the really most visible mega science projects in the country. So, it is one of the mega science projects on Indian soil. So, actually we had to hunt very hard for the right place to locate LIGO India, because LIGO India, as any LIGO detector, is extremely sensitive detector, needs to be placed such that vibrations of the earth are minimal. You have to make sure there are no roads, there are no airports, no other disturbances that man has made around it, which will disturb our signals. So, in fact, it took about 5 years of intense search on 40 sites around the country, where we carried out seismic surveys to determine some of them and rule out others. And finally, in 2016 we have come across a site which we think is the best, and that is a preferred site, and it is also extremely quiet geologically, in the sense that the seismic noise at that site is a few times better than the best sites that other LIGO like detectors are on. So, a lot of action at the site already. We are sort of closing on to start the construction phase. There are kind of sort of trenches being dug to check out the soil, boundaries being marked out, lot of intense activity happening around it. What we have to do next is, once we have flattened the ground, we have to set up a huge vacuum system on that surface. So, entire 4 kilometer of the path of the laser has to be in ultra high vacuum. So, in this figure, where again we show you the Michelson interferometer, you can see that that entire apparatus, which is 4 × 4 8 kilometers long, is encapsulated in a vacuum enclosure, and the amount of volume in that enclosure is 10 million liters. So, this is one of the largest vacuum systems that would be operation in the world. So, it is amongst the LIGO, this is one of the 3 LIGOs are the largest vacuum, ultra high vacuum infrastructures in the world. So, this is how the vacuum infrastructure will look. This is something that industry in India will start fabricating once we test out, prototype some of their constructive capabilities. And this is an immense structure which unfortunately will not be visible, because we will of course cover it up with all buildings, but this is the bare bones vacuum infrastructure that we are setting up here. Then in that vacuum infrastructure, almost like as if we are operating in an operation theater, people have to be working in very careful zero contamination kind of zones, wearing fully garbed clothes and try to set up all the mirrors and the lasers that will, and the suspension systems that goes into an operational detector. The team is building up at a series of meetings that we have had. We have reached out to a large number of Indian institutes. The list is growing, and those list of institutes and a picture from one of such meetings where we are bringing together international experts and Indian researchers together to build up a community of researchers in this field. There is also very interesting science with astronomy that happens around gravitational waves. In fact, the recent binary neutron star merger, there were 10 Indian astronomy facilities which played a role in exploring the physics that happened with the event, which included the facilities like the AstroSat satellite, the Giant Meter Wave Radio Telescope, and facilities at telescopes in Hanle. And so, this is again a project that is kind of reaching out and bringing into its fold people from very distant areas of astronomy and physics. What you realize, and I have not really emphasized that, you should know that this is an extremely data intensive research. So, an instrument of this kind produces huge amount of data, and to process it and to locate signals requires huge computing capabilities, and that is something that we are growing up at IUCAA as we go along. So, here is the picture that I end up with, which shows you actual terrain on which LIGO India will be built. The terrain data was obtained from the Indian Space Research Organization through their Cartosat data, and on that the Tata Consulting engineers have actually sort of sketched out a feasibility of building the LIGO India facility. So, in not so distant future, this is the kind of picture you would see if you were to look at LIGO India from the sky in say 6 years' time. Finally, let me also tell you about another initiative related to gravitational waves, but in a different window. Now, this is a window where we are trying to go for the primordial gravitational waves that are generated at the birth of the universe. So, this is again a pretty challenging initiative, and a proposal has been submitted to the Indian Space Research Organization ISRO, and this is to look for gravitational waves using a natural detector that nature provides us. So, if you are at any point in the universe, we are all surrounded by a plasma screen which is about 43 billion light years, 14 gigaparsecs away from us, and this red shell shows you that IMAX theater. And essentially what happens is, at the birth of the universe, this shell is perturbed and this sort of shakes, and the light coming from this plasma surface hence behaves similar to what the interferometer was doing. It sort of has different distances to you at different times. So, we are trying to look at the warping of this surface warping of this surface of last scattering through a different set of observations, which is using cosmic microwave background. And so, these are maps of the cosmic microwave background, polarization and temperature anisotropy. And if you look at the stick pattern, we are trying to look through these stick patterns. We want to make very sensitive maps of this anisotropy and polarization, so that we can look for world patterns in it. So, if you see the inset that I have just brought up, you will see the pattern of sticks there has very distinct vorticity. They are worlds, as if they are kind of circulating currents, and that is the pattern we are looking at. This wall pattern are telltale signatures of primordial gravitational waves. So, this requires us to really go and look for this is of course something that we need to do in cosmology, and this requires us to again push the boundaries of measurement. Again, this is not length measurements, but boundaries of power measurement. How much power can we detect? So, as I again did in earlier for length, in the dashed box are the powers that we normally encounter in day to day life. You know of megawatt power plants, you have milliwatts in various instruments that you use in day to day life. What is interesting is, you might want to know, your cell phone, when it receives signal, actually is sensitive to 10 to a minus 14 watts. Okay. So, your smartphone is actually an extremely subtle and very sensitive detector. But for what we want to do in terms of looking for gravitational waves from the beginning of the universe is to do much better than that. We want to go again, interestingly enough, to attowatts. So, which is like 10 to a minus 18 watts, and try to detect power in that thing. So, if we manage to do that, this would be absolutely stunning scientific frontier research. It would reveal signatures of the birth of the universe and the quantum gravitational effects. We believe gravitation is quantized, and we will see first hints of that. And this is the quest that we want to undertake in what we call CMB Bharat. And again, it is a constitutional Indian Cosmology Consortium with about 100 members, and we have made a proposal to ISRO very recently. And the proposal is to send a satellite, a spacecraft, to what is called the second Lagrange point. Lagrange points are quasi stable positions in the Sun Earth gravitational potential, which you may recall from your basic science in the early days. And this is the Lagrange point L2, which is furthest from the Sun, and that is where we would send the spacecraft, and the spacecraft will sort of go in a loose orbit around it and point away from the Sun and make very, very accurate maps of the cosmic microwave background radiation. At the heart of this satellite would be a focal plane of detectors, either 2400 monochromatic or dichromatic detectors. You can pack as many detectors as you want. Each detector is capable of detecting powers at the level of attowatts, and you combine all their capability to hunt for this very subtle signal. To do this, you need to cool the satellite to absolutely cryogenic temperatures of 0.1 Kelvin, right. So, in this cutout of the detector, you can see that the sun at the bottom would heat up the bottom part of this satellite to 25 degree centigrade, whereas your detector focal plane has to be at 100 millikelvins, which is minus 273 degrees centigrade. So, these things are again kind of calling for technology at the frontier and the capabilities to do these measurements. This is a satellite which would be about 2 tons, about 4 meters in height and 4.5 meters in diameter. It can be launched on one of the launchers that ISRO has. It would require the most capable launcher, the GSLV Mark III, to achieve the goals of this mission. And this is where I want to leave you with. We had the most recent CMB mission launched in 2009, and we are hoping that India would take lead in the next generation one. I hope I have given you a sort of nice tour of the space-time ripples, how we detect them, the space-time detection, ripple detection through terrestrial observatories like the LIGO detectors, and also a little flavor of what might come in the future, or maybe 10 years ahead, through microwave background measurements, where you reveal the birth of the universe through very, very sensitive measurements. Thank you.